Okay, we're gonna start now. Just share screen. Yeah, okay. Today in our seminar, we have Dilu. Dilu is a PhD student at INPA, under the supervision of Professor Alfredo Yusen. And he's gonna talk a little bit about one of the works of his PhD, finding the convergent circumcenter method for the complexity problem. Dilu, please come here and talk. And then people probably will have some questions. So you have like 45 to 50 minutes. Okay. Okay. Yes. Yeah.
Now, I'm really glad to hear make the presentation. This is about my second paper, and together with Professor Alfredo and Luis Rafael, Union. In this problem, I'm sorry. I just had a fever yesterday, so there are some problems with this. I'm really sorry about it. In this problem, we present a perturbed approximate circumcenter algorithm, which we call it PACA, for solving the convex divisibility problem in Euclidean space. And we have several key points. We have closed formula of the algorithms, later relation convergence, later we prove the linear convergence, and finally the finite convergence. And we use the numerical experiments to prove our algorithm is better among the algorithm which we compared. The convex feasibility problem is a very classical problem in optimization, which aims at finding a point in the intersection of M closed and convex sites, and this problem presents a model for solving many engineering and physical problems, which has widely been used. In this talk, we consider the CFP in the form of function inequalities, which means the size is in the form of a convex function inequality here, and where f is convex function. This formulation does not impose any limitation in principle, as we can always choose the fi equals to the norm of the distance between the x and the projection onto Ci. And we have in this paper we have this function. Always we have this function which is for the later point. We always assume that there exists x hat belongs to R and such that x hat is strictly less than 0 for all I equal to 1 to m, which means the interior of the intersection is non-empty, which is necessary for the perturbation for the convex site. Yeah, in the beginning, the circumcenter reflection method was first proposed to accelerate the Douglas-Richford method and the method for Nerting projection method. We know that the Douglas-Richford method was first proposed for solving the heat equation, and later it has been widely used both for convex divisibility problem or for finding the 0 point of sum of maximal monotone operators. For the convex physics problem, the Douglas-Richford method is like this. At the current iteration xk, we first do the reflection to set A. You get this point, and then consequently we get the second reflection point here. We get this point. Then we take the midpoint of the xk and the second reflection. So this point is the next point according to the Douglas-Richford method. And in this case, we just make use of the information of the original point and the secondary reflection point. But why didn't we make use of all the information of 3 points? So that's why they use the circumcenter. We just calculated the midpoint, not only of these 2 points, but also these 3 points. But the midpoint does not make any sense here, so it becomes a circumcenter. And for solving the convex feasibility problem, Douglas Richford method does not perform always well. For example, if we have 2 convex sets here, if the initial point is very far away from both of these sides, for example, the initial point is here, and then we do the first reflection, it may get the other side, but also very far away. And then we calculate the secondary reflection, it may come back. So if we just calculate the midpoint here, so this midpoint does not prove very well. But if we take the circumcenter of the origin point, first reflection, and the second reflection, here is the midpoint. If we calculate the circumcenter of all these 3 points, it would be somewhere like here. So it would be much better than Douglas Richford method. Okay, so the circumcenter is defined by this. If we have x, y, z, the circumcenter of x, y, z is the point which lies in a fan subspace given by x, y, z is equivalent distance to this point. So the circumcenter reflection method is determined by this operator. We call this TABC, the circumcenter operator with respect to A and B. Here, the RA is a reflection which depends by 2 times the projection minus identity operator. One limitation of the circumcenter is the convergence requires one of the sides to be a manifold. It has been proved, a counterexample has been proposed that if for 2 general closed convex sites, it will not converge. So if we want to use the CRM to solve the general convex feasibility problem, we need to use this called P-area product space, which first we define C is a product of C1 to Cm, and D is a diagonal subspace, which also belongs to the R and M. And so the original problem, if we want to find a point x star belongs to the intersection C, is equivalent to find a both base Z star, which is in this form belongs to the both face Z and intersection with both face Z. So with this kind of product space technique, we can solve the M-set convex feasibility problem with this kind of product space. Yeah, all aforementioned method, I mean, no matter it is Douglas Richford method or theorem or the map, which requires the exact projection. But the exact projection somehow is very expensive when we calculate in practice. Even if we just calculate a very simple case like ellipsoid, we do not have a closed formulation to calculate the projection onto an ellipsoid. In our numeric experiments, when we calculate the projection to ellipsoid, we use the EDI. It is not so slow, but it requires a lot of time to calculate the projection. So as we just want to save more time when in practical situation. So we just want to use the proximal projection. So this CERM replace the exact projection onto the original site with some projections onto the site in them, like the half space, condition product half space, which is easy to compute. It's like this. For example, we have two sides here. We have a point here. We calculate. This is a half space which contains this site A. We just use the exact projection to this half space as the approximate projection to this space A. So this is what they in this CERM, the approximate circumstantial reflection. It was applied in this way. If the CI is in the form of convex function T positive, which is presented by the function, then we define this site. If the xk belongs to Ci, it is Ci itself. But if otherwise, it is defined. We define Si in this kind of formulation. Actually, it is a half space defined by the UI. Sorry, UI here is the subgradient of Mi at point xk, which is the half space contain the Ci. And since we know the exact projection onto this half space, we onto this half space, we have this kind of exact formulation of the projection. We can calculate the projection, the exact projection to this Si very fast. Since we can have something similar with it like this. We can calculate with the closed formulation. So with the definition of this Si, we can calculate the projection of Si as the proximal projection to the Ci. Okay, since we have the site Si here, we define both ways as which is product of S1 to Sm. So we can apply the CRM for this both ways S, which is in the product phase and the diagonal set U. It has been proved that the sequence generated by CRM converges to a point intersection linear. Okay. Next, I will introduce our algorithm Paka, which will have the finite convergence. First, we need to define the perturbed convex site CIK like this. Fi is a convex function, and epsilon k is a perturbation parameter. Here, I need to mention a little bit about the later points. For example, if the intersection of two convex sites is the interior of the intersection of the two sides is empty, in this kind of situation, we cannot do this kind of perturbation. Because if we do the perturbation here, this is side A, this is side B, we do a very small perturbation, then the A will become in this kind of situation. B will become in this kind of situation. So we do not have the intersection anymore. I mean, for small enough, it should be. But if the intersection is, the interior of the intersection is non-empty, like this. For small enough, it's okay. If we do the perturbation, the intersection would still be non-empty. So that's why we always require a station point in our algorithm, since we needed to do the perturbation here. So we can define the SI here similar to the SI before. What we only need to do is here we just put the perturbation parameter into K here, which this Newton K approaches zero is and always be positive, always positive and approaches zero. And then we use the exact projection onto SIK as approximate projection onto CI. Then we define the both phase SK as the production of S1K to SMK. Then we utilize CRM to the both phase SK and the diagonal space U here. Since if we want to CRM to the MSET CRM problem, I mean the general CRM problem, CFP problem, we need to use it with the product space. And this both phase SK is in product space, and this U diagonal set U is also in subspace in the product space. Okay, here is the steps of the algorithm. First, we have an initial point. Then we calculated this VIK, WIK, alpha k, and then we can calculate the xk plus y equals to xk alpha k wk. And wk alpha k is a scalar which produced in this form, and the wk is a vector which could be calculated in this one, and VIK is in this one. Actually, VIK somehow is related with the projection of SIK. Is a part of the projection onto the half space which contains the set CI. Yeah, this is the stopping condition. If the xk belongs to the intersection, then we stop. Yeah. Since our algorithm has a finite convergence, after some iterations, the point xk will lies in the intersection. Yeah. Before introduce the convergence result, I just need to say something about the classical methods. How to prove the classical methods? I mean, related with the CFP, like the map, like the dot switch code. To prove the convergence of this kind of method related with projections, we always use the OPL lemma. The OPL lemma in Rn in the Euclidean space, which requires two conditions. First, we need to prove that the whole sequence is feature monochrome, which means the sequence will get closer and closer to the intersection. And second, we needed to prove there is one clustered point which will light the intersection. Then we can use OPL lemma to prove the whole sequence converges to a point in the intersection. But here we cannot use the OPL lemma directly. The problem is we cannot prove our sequence is feature monochrome, because if we want to prove the sequence is feature monochrome, we need to have a fixed set. For example, if we want to prove the set xk is feature monochrome with respect to this set, this set A should be a fixed set. But in our case, at each iterator, the site has a perturbation, and the perturbation parameter is not the same. So we cannot, it is very hard to get the feature monotone with respect to a non-fixed site. So we need to do something, we need something new instead of feature monotonicity. But but very similar like with monotonicity. Here we proposed a new definition which called the feature start monotonicity, which is M is a subset of Rn and Yk is a sequence. We see that Yk is feature start monotone with respect to M. If for any point Y there exists a positive number in Y such which guarantees this. Actually, this is quite similar to the with respect quite similar to the with monotonicity. The difference here is this there exists a positive number in Y here, and for all K is greater than Y. Here is the difference because the site changed in every iteration. So we just needed this. And since we have the definition of the feature start monotone, we have some properties of the feature start monotone. So if the sequence Yk is feature start monotone, first the sequence is bounded. Then if there exists a cluster point Y bar which belongs to M, then the whole sequence converges to Y bar. Actually, the second one is in some sense another kind of Opel line, but with respect to the feature start monotonicity. And the third one is for the convergence rate. If the sequence converges to Y star in M, and the distance sequence converges Q of R linearly with the constant eta, then the sequence converges R linearly to a point Y star, which with the same constant. Okay, next I will introduce some the convergence theorem. The first is consider the CFP with the CI of the function in quantity form. Suppose xk is generated by Parka with any initial point. Then the sequence, if the sequence is infinite, then we can prove that xk is feature start monotone with respect to the interior C. Here we cannot prove that the feature start monotone with respect to all the sides C, but only the interior of the C. And then this one is very easy to get if we have the feature start monotone. The distance between xk plus 1 and xk would approach 0, and then the sequence, and then the third one, the sequence is bounded. Actually, the idea of to prove this algorithm is use the product space technique and some properties of the CRM algorithm. Okay, since we have the we need if we want to prove this one, we need the product space and this following lemma. This following lemma is from the CRM paper, which means the circumcenter of A and B of X with respect to A and B is a kind of production of X to the HX at intersection with B, and we also have some causing inequalities like this. Okay, since we have the feature start monotonicity, we can prove that the sequence xk generated by Parka, if the xk is infinite, the x bar is a cluster point of xk, then the xk belongs to C. How to prove this? We just use the closed formula of Parka and the Slater point. Okay, next is the main theorem of our paper. let xk be generated by Parka from an arbitrary point. If xk is infinite, then it converges to some point x star. Actually, the key point of this algorithm is theorem 7 is lemma 6. We need to prove that if the xk is infinite and x bar is a class point of xk, then it belongs to the intersection, which requires some calculation just by using of the closed formulation. It is not very easy, but not difficult. Yeah, next I will introduce some the convergence rate. Before prove the linear convergence rate, we just need some lemma about the distance sequence. The first is the distance sequence is something like all the non-extensiveness. It's like this, and another one is like the relationship between the distance sequence and the difference of xk plus 1 minus xk. With these two lemmas, we can get that if the xk is infinite, then the distance sequence convergence Q linear. And then with this one, and with the property of the phase monotone sequence, we can get that the xk and generated by Parka, if it is infinite, then it converges R linearly to the to a point x star in the intersection. Then I will say something about the finite convergence. The finite convergence relies on the perturbation parameter, relies on the velocity of the perturbation parameter approaches zero. If it is summable, then it is finite convergence. If it is unsummable, we will have the finite convergence. If it is summable, which means it approaches zero quickly, we will not have the finite convergence. We only have the linear convergence rate. So under this later condition, if the sequence convergence and the sequence is infinite, then we can prove that the perturbation parameter sequence is summable. So according to this lemma, we can see that under this later point, if the sequence decrease zero and if it is unsummable, then the Parka has finite convergence. Which means there exists some index k such that xk solves this CFT problem. To prove this finite convergence, we have some. This is just the outline of the proof. First, we have this one, and then we can have the inequality of the delta k plus 1. Delta k is the distance between xk and ck. And then we use the subgradient inequality. And then we can get the inequality about the h2k and the delta k. Then we can get the sixth one, which the sixth one has already shown that the h2k is the summable, yeah, because it's less than the delta n. N is some fixed positive integral. And this lambda k to the power of k minus n. So this already proves that if the sequence is finite, the h2k will be summable. Okay, we just compared in the numerical experiments. We just compared the Parka with the theorem in product space and the simultaneous subgradient methods. And the modified cyclic subgradient by subgradient projection method. For the perturbation parameter, first we use 1 over k, and second we use 1 over square root of k. And the problem is we apply all these measures for the CFP with a ellipsoid, and the ellipsoid is in this form, which is like in this form, and we generated the ellipsoid randomly. Actually, here is Parker 1, Parker 2, the CSPM 1, the cyclic CSPM 1, CSPM 2. Both of these two methods and these two methods have perturbation and the perturbation parameter. Yeah, here is the performance of all these seven methods. We can see that the Parker 2, which with the parameter 1/square root of k performs better than all the other algorithms. And here is the table about the CPU cap. We can see that the Parker 2 performs best among all these algorithms. And here is also the CPU cap. We can see the Parker 2 performs best, also performs best. There is one problem here that since we do this is the perturbation set of CI. We call it CIK. Actually, somehow, if the initial point x0 is very far away from the intersection, the function value would be very large. I mean, compared with the perturbation parameter. So somehow, maybe in future we can propose some strategy to choose the perturbation parameter. I mean, which would compare with the function value. I mean, if the function value is like 10 to the power of 6, even if we choose it like 1/square root of k, it will be much more, too much small compared with the function value. So the perturbation do not impact a lot. But in our numerical experiments, we unfortunately this 1/k performs very nice. I don't know why. Even if we choose the initial point very far away, but this performs very well. Okay, here is the reference of our paper. This is the CRF paper, and this is the approximate CRF paper. This is our finite convergence paper already on the arcade. Okay, that's all. I'm really sorry about my situation today, so I didn't feel very good. So I apologize for that.
No, it was all good. That was very good. Let's think. Okay, will we have any questions? Suggestions? Felipe, you turn on your camera. We can see you.
Just turn it on, just to see you. Just see you seeing that I am here.
Oh, okay. There's no
Yeah, but
question.
I have a very easy question, just something. If you can come back to the slide where you have the sets that you are projecting on.
You mean when he showed the Douglas Rashburn method?
No, on the beginning of the presentation.
Oh yeah, that one.
That you have two cases, CK and the other one.
Oh no, okay. It's the
linear approximation.
And the approximation, the CK, the one that I did. The linear approximation of the sets. Is this sorry. So No, so this one.
No,
Oh, come back.
back. Earlier than this. Earlier. Before that, when you have the just this, sorry, I think that one. Yes, this one that you have S and this.
Yeah.
You are projecting it on S, okay? Isn't it?
Yes.
And if you have just the second equation of 11, won't it be the same? Because if xk is on C, I think that it will fit the inequality because f will be negative, and then you have exactly the same projection. So I think that you can just write the second equation, isn't it? Just
Question?
Yeah. Ask why we defend the SKI like this, yeah.
Yeah, he said that maybe the last equation was enough.
Yeah. It's
Okay, got it.
not something important. It was just because Rafael called my name, and I when I look at it,
Let me see a little bit. I mean, I think if you have only the second inequality here, but if the xk already belongs to ck, you do not need to do this calculation. I mean, if the xk belongs to this side cik, you can always define this half space, yeah. You can always define this half space and project onto this half space, but it's not necessary because the side is the point x is already belongs to this side.
yeah.
It is you can do this, but
Because I think it's defined in this way, because then you don't need to compute the subgradient. That's why it's like this. But I guess it could be the same, but I'm not sure if it's always the same. Depends on the subgradient, because it can be between the CK and the border of the hat space. You mean, you know what I mean?
I think that the linear approximation, if you are already on the set, the linear approximation will pass by the points that you have. That's what I was thinking.
Yes, you're right. Yeah.
Okay, but as I said, it's not a serious issue. It's just because Rafael told me my name.
Yeah, the point here is that you don't need to project. You don't need to use the linear approximation.
Yeah.
That's the point here. Yeah.
Yeah.
You might be right. It may be the same. Any other questions? Yeah.
It's more a comment than a question. You said that if your x0 is far away, you have some problems when you're in the beginning of the method, right?
it is just for the Douglas-Richard method.
Oh, okay.
Not our method, not the circumcenter method.
Okay.
All the methods related with circumcenter do not have such drawback. Only Douglas-Richard method.
Okay, but when you prove the convergency of your method, you take equally weights the vertices.
Yeah, you're right. Yeah.
You could take complex combination.
But it is one, because it's the point that lies closer the point that you are on the affine, but it's kind of like a convex combination. Yeah.
Yeah, I know what you mean.
Yeah, yes, if you have information of this set is bigger than the other one, you could move the where you are next to the
Yeah. Like what you said, maybe we can take the combination of the 3 points. Yeah, it will be a more general situation, But why I think Luis Apel and Rodriguez and Junior they proposed the circumcenter method at the beginning is this kind of circumcenter point is a very special among the convex combination, which has a very nice property. So you can take the you can take the general convex combination, but as long as you take the circumcenter, you will have some more developed properties, more nice properties. But if you just take the they have another method called the CCRM, which is called the centralized circumcenter. If you take the circumcenter, you will have the superlinear convergence. But if you just take the circumcenter, you just take the convex, any general convex combination, you will lose the superlinear. So this special convex combination, which is called circumcenter, has its advantages.
Thanks.
We have time for one more or two more questions. Gabriel, are you using the product space?
Yes, this is a very nice question. Actually, we only use product space for proving the algorithm, for proving the here. We just use the product space for the proving of convergence result. Actually, in the algorithms and in the numeric experiments, all the point is in the Rn, not the Rn times m. This we should send this to the function value, to the convex function inequality. Since we have this convex function inequality, we can avoid using the product space. But since we use the circumcenter method, CRM method, as long as we want to prove the convergence result, we need the product space to prove the result. But in the practical calculation, we do not calculate in product space.
And I don't quite understand why you don't need centralization.
Centralization in this method, because we just use the CRM, not the
Because of the product space. And the product space I don't need to. So the main point here is that but you don't use the product space. Not well, the reason you don't use this, you are using the product space. The major breakthrough here is that you have the closed formula that you don't need to compute on the product space. That's the difference here. So the closed formula to compute that closed formula is the difference. This is alpha k. So you just compute it, and this is much cheaper than computing on the product space and doing the CRM. So it's like an implementation of the product space, but yeah, for this particular case, it's better. And the epsilon k there sequence gives you the final. So if you take epsilon k as 0, this is exactly the same product space. And I made this. We run the test, and it's exactly the same point, but this is contracted because of the closed form. Yeah. So this is also a major breakthrough in the practical sense. Yeah, because of the closed form.
You can see all these parts, all these WK, VIK is in Rn, not in product space. So the XK and XK plus 1 is in Rn. The product space just for the prove the convergence.
So yeah, we avoided this in the practical sense because of this form. It was very nice. Yeah. Do you have? Yeah, Francisco, you have any question?
Yes, if I can ask, could you say, just explain me to give an idea of the parameters of the linear rate convergence? I see the M, which I think is the number of sets, and then we have beta and sigma. Could you give me just an idea of what are they related to? I don't know, usually in the previous work, they were the angle between the sets or something like that.
Linear convergence. Yeah.
Yes, the rate, the linear convergence rate. Yes, this one, 18.
Feedback, come back.
Yeah. Could you just give me an idea of beta and sigma?
Sorry, I just forgot to put the beta is the boundary of the subgradient. We know that the subgradient of a convex function is local bounded, since it is the maximal monotone is local bounded, so the subgradient of a convex function is local bounded. When we talk about the convergence rate, we talk it in a small neighborhood. So this beta is the boundary of the subgradient, and this beta, let me say sigma. Sorry, sigma. This sigma.
Don't worry, I was just curious because in the previous work I remember that there was some angle between the sets. I remember that the Friedrich angle or something like this, and I was just curious of.
Yeah, it's related to the error bound that we are assuming between the sets. So not only we're assuming Slater condition, but we're assuming some error bound, and the sigma is some computation of the constant that is related to the error bound. So it's kind of angle, but in the more general sense.
I see. And M is this number of is the number of sets
minus the parameter of the error bound that we're assuming to the power of 2. I guess it's something like that. Yeah,
okay.
right.
Okay, thank you.
So we have also another question, maybe the last one. Yasir, please.
Yes, thank you, sir. It was a nice presentation. Mr. Lee, I have one question to you. Please tell me, is there any possibility that we can achieve finite convergence of Paca with weaker conditions than Slater conditions?
Can you repeat again, please?
Weaker is later.
Oh, okay. For final.
Without the Slater condition. I don't think so. Without the Slater condition, we can get the finite convergence result. The finite convergence result requires two. One is it requires the set Ci should be in the form of convex function equality, like f(x) less than 0. This is the first one. Second one is it requires a perturbation parameter approaches 0, but ensemble. If we do not have the Slater condition, when we do the perturbation, it will not make any sense, since as I said in the beginning, if we do not have the Slater condition, we do the perturbation, the intersection of the perturbation side will be empty. The intersection of the perturbation side will be empty. So we cannot do the theorem. We cannot solve this kind of problem with the empty intersection.
Not with this backup, no, yeah. I guess you will only get linear convergence. That's the paper that we have with Karn. because we don't need to assume slavery condition, only
Yeah.
the error bound.
Yeah.
Sometimes can be the same, but not in that case, it's not. So I don't think you can get finite convergence without assuming that.
Yeah, actually, when I do the proof, when I write the proof for the finite convergence part, I just realize it do not depends on the different algorithm which we use. It only depends on the formulation of the site. So maybe it is possible you can prove like finite Douglas Rexford method, finite map, finite simultaneous projection method. The finite convergence part only depends on the Slater point, Slater condition, and the formulation of the site, which is like the convex inequality function. It does not matter which method you use.
Yeah, but for the convergence of this, you need the error bound. That's why you need the solution. Yes, sir. Do you have any comments?
Yes. No, thank you. All right, sir. Thank you so much.
Okay.
I got it.
Okay,
Thank
so
you
I
so
think
much.
thanks again, Dilu, for his presentation. See you next week.